Hello? Okay.
So our second speaker this morning, Julian Sahasrabudhe from IMPA. And I'm sorry, I forget his title. Sorry.
Okay. Okay. The title is a bit confusing, I think. I shouldn't have called it that. Yeah, so let me start by saying thanks to the organizers. This is somewhat of a strange problem, perhaps, but I think it actually is situated quite naturally, and I'm quite fond of this problem as when you're thinking about it, it brings you close to some mysterious things about triangle-free graphs that have some kind of, that are sparse and have some kind of pseudo-random property. Not the pseudo-randomness per se, but some kind of pseudo-random property. So the story begins with the radiograph. So what is the radiograph? It's an infinite graph on the integers n. Maybe goes on and on. And it's a cool graph. And what property does it have? It has the property that no matter what countable graph you give me, I can find an induced copy inside of the radiograph. And in fact, it's the only countable graph that has this property. So it is universal in some sense. And what really drives the universality of this graph is what's called the k-extension property. Well, I'll call the k-extension property. So what is the k-extension property? The k-extension property is, so the radiograph has the following property. Whenever I take k vertices in this hand and k vertices in this hand, there exists a vertex somewhere in the graph, that joins to everything here and to nothing here. So this is the k extension property. Actually, sorry, I lied slightly. I'm gonna say I want the sum of my two sets to equal k instead. Oops. So I have these guys and these guys, all distinct vertices. Implies there exists a z that joins to all the x's and none of the y's. Okay, so this is really what's at the, in some sense, what's at the heart of the radiograph. And what's interesting, another interesting property about the radiograph, I'm not going to say exactly what I mean by this, but the radiograph can be approximated by finite graphs. What do I mean by that? There exists larger and larger finite graphs that have the k-extension property. And these are actually our friend, the GNP, or GN1/2. So GN1/2 observation is that GN1/2 has the k-extension property, well, not for all k, obviously, because it's a finite graph, but for all k up to log n. So has k-extension property for k all the way up to some constant log n. Probably the constant's 2, actually. Okay. But where things are getting more interesting for us is when we talk about triangle-free graphs. So there exists a sort of triangle-free analog of the radiograph. And what is it? It's just there is some graph for which, again, a countable graph that's triangle-free, and it has the property that every countable triangle-free graph you give me, I can find as an induced subgraph of this graph. And we really start our question today is there a finite way of approximating this graph? Okay, so let me back up for 1 second. So similar to the k-extension property over in this old world, there's a natural k triangle-free extension property. So here's my k triangle-free extension property. And what is it? So this is just the property that's really driving this triangle-free analog of the radiograph. It's absolutely trivial to construct, absolutely trivial to construct. But it has the property that whenever I take k vertices in this hand, k vertices in this hand, there's a vertex that joins to everything here and nothing here, as long as these guys are an independent set. Otherwise, I would have created a triangle. So that's obviously illegal. So same as this thing, but x1 up to xa are an independent set. And again, this is really the property that's driving what's interesting about this graph. And the question that we begin with is a question due to Cherlin. It's kind of a weird division here. And this is a really lovely, comes from the 90s, perhaps 93, let's say, who asked, for every k, k is 10 to the 10, does there exist a triangle-free graph with the triangle-free extension property? So it's an incredibly stupid question. I mean, in the best possible way, right? So, yeah. So does there exist? And this is what he calls the name of my talk: existentially complete triangle-free graphs. Does there exist a triangle-free graph with the k triangle-free extension property for every k?
You mean finite graph?
Sorry, yeah, thank you. Triangle finite graph, yeah. Yeah, so we know that it's I mean, again, trivial to construct an infinite one. Is there a finite one? Thank you. It's kind of interesting. The motivation for these things comes, and I don't totally understand myself, but it's something about creating good models for certain kinds of logics. And this corresponds to finite model property. But in some sense, I think it's an interesting property, and it's a sort of quasi-random property on a local sense. So I'm sort of looking like a random graph at a small scale. Okay. So in 2010 or so, Cherlin wrote another article sort of summarizing what's been learned about this problem, the state of affairs of this problem up to that point. And it's basically this. So 1 is trivial. You can do it. 2 you can do without too much difficulty. 3, there's a bunch of not easy constructions. So you take some clever objects, put them together. There's some results when you add tons of extra properties to this, saying that they don't exist. But for k equals 4, it's open. So even this problem for k equals 4, any graph in the entire world you can think of, it's not known if it has that property. And I should also say that this problem more recently has made its way over to graph theory by way of even Zohar and Lineal, who's given a whole bunch more examples, but again, only for the k equals 3 case. So I'll put even Zohar and Lineal. Also have some results about constructions. And so let me just define a function, f of n. And this is going to be the maximum k so that I can find a triangle-free graph a triangle-free graph with the k extension property. Triangle-free extension property on n vertices. The maximum k such that there exists a graph, free graph G with the triangle-free extension property. Sorry? Question? Ah, thank you. On n vertices. And even Zohar-Lineal will conjecture that, given the sort of ruinous state of affairs on the existence of these graphs, maybe they just don't exist for large enough k. So they conjecture that f of n is maybe just bounded by a constant. So I should also say that, as a side note, taking a sparse random graph does not work. Because for these to exist, the maximum degree, and in fact, you should have a fair number of vertices that have degree about this. So 1 minus little o, 1. Something going to 0 in k. So in some sense, this rules out immediately what you might think by going, great, let's take a sparse triangle-free graph. This is sort of a side note for what you might be thinking. And the main theorem that I'd like to talk to you today about is some progress towards this conjecture. So, and this is joint work with Shoham Lester. And we show that f of n is at most 8 times log n over log n. Okay. So in some sense, this doesn't seem very impressive in the sense that log n over log n, can be a little bit bigger than 4 most of the time, which is really the state of affairs. Yeah, OK, wonderful. Yeah, so maybe something that is interesting about it is it really genuinely separates it from the version of the problem without the condition on triangles. So this is saying to us, triangles really do come into the mix. They are ruining this sort of local pseudo-random property at least that much. Probably a hell of a lot more, but at least this much. OK. And another reason I think it's interesting is in order to prove this, you have to think fairly hard about sparse triangle-free graphs with some kind of pseudo-random property, which to me at least I think are sort of a mysterious and interesting object. Okay. So let's just quickly get on the same page. I'm going to note first, so this is really a sanity check, just to see where we're at, to see what's obvious. So note that, oh my god, f of n is at most log n, base 2. And what's the proof of this? OK, you can do a tiny bit better than this. So here's the proof. You give me a triangle-free graph that you claim has the property for log n plus 1. Well, it's a triangle-free graph, so it has a big independent set. It doesn't actually matter how big, but you have a log n plus 1 sized independent set. And now, since you have this property, the neighborhoods of the graph shatter this set, which is just a fancy way of saying for every subset of that, I can find a vertex with exactly that neighborhood. But then I've just found 2 to the log n plus 1 distinct vertices in my graph, which is a contradiction. OK, so this proves this. But also note kind of how we lose control of this argument quite quickly. So, so let's just set for now, I'm thinking always k is about epsilon log n. And let's try to repeat this argument in this regime. So I'm just a tiny bit below, in the constant. And now what I can do is I only find, so I'm just looking at some set. I'm shattering the set of size epsilon log n. And all I get out here is a set of size polynomial in epsilon. So in some sense, great. Who cares? this is actually not a very big set. Maybe there could exist such an object if you can just sort of pack these together in some clever way. OK. So what's the main obstruction? What's stopping us from getting up to log n? So here's the picture. So to sketch the proof, I'm going to be extremely optimistic, and I'm going to hope that I have the following situation in the graph. So you give me your amazing triangle-free graph that has the k extension property for k like that. Suppose I could find some very small, it's hard to say exactly what size. In fact, size we don't have too much control over what sizes are. But let's just assume that we have blobs of, size about n to the epsilon and n to the epsilon, about this size. And here we're being incredibly generous. Suppose that between here, this graph is genuinely random. So I have this genuinely, and say p is a half. Okay. So I can find this very small, random bipartite graph. Okay. This is the picture that I want to look at. But why does this even make any sense? Why would I hope for such a thing? Right? Suppose I gave you the problem. There's an independent set. OK, well, now I have all these k tuples in here. I guess tuples like that in here that I need to cover. What's the best way to do that? What's a very efficient way to do that? Well, there's lots of different ways. But a lot of them involve just taking each vertex here as having a random neighborhood. Then the neighborhoods are relatively uncorrelated, and you do a very good job at covering this. So this is at least kind of what you might expect. There's lots more ways to construct, but they all have this kind of flavor is that neighborhoods are very uncorrelated, and so you think maybe somehow it looks like this picture. So what's wrong with this picture? OK, I'm going to draw it a bit bigger over here. OK, so observe. So this is now, this is a familiar situation, right? So this is just p1/2, m bipartite. And now what I want you to consider is k about delta log n. And what I'm going to do is consider cross-independent sets. So I'm going to take some vertices here and some vertices here. And I claim there's actually quite a few of these guys. So there's lots of sets of about this size that are independent, and they look like this. So lots of k cross independent sets with k like delta log n. OK, fine. And the other observation is that if you go a little bit bigger, if I'm in a range about c1 log n, where c is a bigger constant, there's guaranteed to be an edge between these two sets. Okay. So if A prime A, B prime B, sub B about with A, roughly B, roughly C log n, not independent. OK, so here's where the structure comes. If I have a vertex out here, so there's lots of nasty cross-independent pairs here. If this was genuinely in your graph, you somehow have to cover them. OK, suppose this guy up here, this vertex W, is covering some of these pairs. OK, so it has some edges here, and he has some edges here. But since the graph is triangle-free, one of these neighborhoods has to be small. Otherwise, I have an edge like that, and I have a triangle. So what's really the problem for this is I have way too many pairs here to possibly be covered by the vertices in the graph, because each vertex can only cover so many by this restriction. Okay. Okay. So while this is a nice heuristic picture, we've assumed really a hell of a lot about what the graph looks like. And what's most difficult going forward is we really don't have a good notion of what size is. So for example, you might want to say, great, let's look at a dense bit or some dense clump that covers this. But it could be that I have lots of vertices over here that have lots of edges here, but the neighborhoods are sufficiently correlated that they're actually useless in covering this thing. And in fact, it doesn't look random at all. It also could be that, that while the set that covers it is quite large, there exist sort of smaller correlations. Right? So it could be that I split off in order to cover just tuples like this. I sort of split off these into different groups and now cover these independently with totally different clumps of totally different densities in totally different ways. So the problem is really working and getting a correct measure that works for you, because in some sense we don't know the scale that anything's happening at. Okay, so hopefully in the next couple of minutes I'll hopefully introduce what this notion of scale is, which is maybe the most interesting part of going forward. Okay, so let's call a graph G. I have a bipartite graph. Right. Just sort of abstracting my situation over there. I want to call it ST separating if every time I take some S set here and a disjoint T set here, I can find a vertex that covers everything there and nothing there. Okay, just abstracting the situation here. So is ST separating? Oh, sorry, separating. Right, so does everyone understand? So for any time I choose an S and a T disjoint, where S is of size S and T is of size T, there exists a vertex that covers the S and not the T. Okay. So now my first sort of observation I'll call it a lemma here, is that this notion here of being small and not covering many pairs. So if you're not very large, my argument that said that this couldn't happen in your graph was basically because the neighborhoods were too small and there was way too many pairs. But what's nice is this notion generalizes, in fact, immediately to just these neighborhoods being small with respect to a particular measure. And that just sounds like a very pretentious thing to say, but we'll see that we need to use a weird measure to work with this thing. Okay, so suppose let G be an ST separating graph like this. ST separating. And suppose I'm given a probability measure on A. Then, if all the neighborhoods of B are small with respect to this measure, B has to be quite large. Then if the measure of all the neighborhoods then B has to be quite large. Okay. So this is actually quite, in itself, quite easy to prove once you have it. But the point being is this kind of argument generalizes to a more general measure. OK, so what is the right measure? What sort of... I'm so sorry. This should be S here. So yeah, as you'll observe, for this part, T doesn't actually matter. T doesn't matter. It comes in other parts, but then I have to define covering, and then it's confusing. OK. So what is the measure that's capturing how well a set is at doing at covering the other side? So let me define the following. So again, I'm going to be in the same setup. I have a bipartite graph like this that's ST covering. And now I'm going to define a measure mu on B that's going to say how well a subset is doing at separating stuff on that side. So let mu star be, let's just call this the separating. And it's a measure on B. So if I'm given some subset of B, define this mu star of B. And I'll just tell you what it is by a way of sampling it. So here's how I'm going to define this measure. I sample a random S and a random T disjoint. This set over here is ST separating. So there exists some vertex that hits everything in S and nothing in T. Choose one of those vertices at random. Right. So the measure of this set is just the probability that in that process you landed in my subset of B, B. So again, I choose some subset of S and some subset T. I just now choose something randomly that covers S and not T, and I ask, what's the probability you fall into that subset? What this object is doing is sort of measuring how well B does at covering the left-hand side.
How does mu star depend on mu?
Sorry, so this is actually the measure. So I'm defining this measure mu.
Different from when you define mu star.
Yeah, mu star. Sorry, so mu here is just some abstract measure, which ultimately you use as things like this.
My question is, does mu star depend on mu in some way?
No, no.
Okay.
This is a measure that I'm defining. Yeah.
Okay.
Yeah. OK. Great. So I'm running out of time, but I can at least say one more hint at why this is a good object to work with. And I'll put it just in the form of a lemma. Let me just sketch first, very quickly. So just redraw my picture. So back when we really genuinely knew things were random, and here's my vertex coming in, trying to cover stuff on these cross pairs. OK, so covering stuff on both sides. These cross-independent sets. OK, let's first unveil the neighborhood from W to one side. In the case that this is a random graph, if this neighborhood is large, like in a traditional sense, like lots of vertices, then we know that this neighborhood is going to hit a hell of a lot of things on this side. Right? So the neighbors of things in the neighborhood is essentially everything. And since my graph is triangle free, I know that already before even unveiling W, I'm forced to have the neighborhood of W live in this small set. And that's restricting the number of pairs that I can cover, the number of these cross-intersecting pairs. So lemma 2 is just saying that actually having large measure with respect to this particular separating measure means your neighborhood has big expansion. So it means the B has big expansion. So again, this is actually not hard to prove, but I mean the lemma. So again, same setup. let G, A, B, E be ST separating. And here I'm going to let this mu star being the corresponding separating measure is the separating measure on B. If mu star of B primed, here B primed is some subset of B, if this thing has a big measure, so for any epsilon, then it hits quite a few neighbors on the other side. So the union of all x and b prime, the neighborhoods of x, is at least 1 minus 1 over s, okay, some number times a. So sort of hitting almost everything on the other side. Okay. So I'll stop here, but the upshot is that there's still more to do to put these together. But the key idea is really to ditch this notion of size in terms of counting actual things, but instead measure depending on how well sets are doing the covering. Okay, thank you.